Hello and welcome to our first look at wave optics. I just can't get away from the Falstad ripple tank. It's perfect for so many of our purposes. The purpose of this presentation is to investigate the famous two-slit interference pattern, or two-source interference pattern. Let's go ahead and start with just two sources. You'll notice that they're producing waves in phase. That's another way of saying that their inherent phase difference is zero. We can clearly see the wavelength here. Let me pause. The wavelength would be the distance from one bright band to the next. That's the crest to crest distance, or the valley to valley distance. We've already talked about the fact that there are hyperbola of constructive, I should say max constructive and max destructive interference. We call those the nodal and anti-nodal lines. And these two sources could be sources of waves of any type, as long as the medium obeys the principle of superposition, which is true for longitudinal waves in air, electromagnetic waves in vacuum, water waves on the surface of water, and likely various types of waves in solids as well. But the one we care about the most is electromagnetic waves, because after all, we're moving on to the section called wave optics, and optics has to do with visible light. But this would hold just as true for radio waves, X-rays, well, maybe not so much X-rays. Quantum behavior becomes more important when you're talking about shorter and shorter wavelengths. In any case, what do we observe about this two-source interference pattern? Well, why don't we start by changing some of the aesthetics here. If you make it a little brighter, it makes it easier to see the nodal and anti-nodal lines. If you increase the resolution, that also has the effect of zooming out, which is good because when we look at the interference pattern from a double slit, we're really interested in the far field pattern of interference. That's where the observing screen is rather far from the sources. Or you could say the distance from the sources to the screen where we observe the pattern, that distance is much greater than the separation between the sources. So we're going to use the letter lowercase d to describe the separation between these two sources. And let's think of these now as sources of visible light. Now, it's not actually very common to have an isotropic source of light of one frequency. Sure, a light bulb pretty effectively radiates light in all directions, but that's not light of a single frequency, and it's certainly not what we call coherent light. A laser is a great source of coherent light at one frequency, but that tends to be a beam rather than an isotropic radiator. Okay, let's change just two things here. We'll start by changing the frequency and try to observe what happens to the spacing of I'll call them the nodal lines. That's the directions of destructive interference where it's kind of fuzzy and less bright. Watch what happens to that spacing as we increase the frequency. And increasing the frequency, of course, means decreasing the wavelengths. So what happens to the spacing of the antinodal lines and the nodal lines as we shorten the wavelength? Here I go. You can see the wavelength is definitely getting shorter. Can you see what happened to the spacing of the nodal lines? They're actually so close together, it's almost difficult to see. So how about I back up a little bit? I may have gone a little too far there. I can also play with the brightness. There we go. Hopefully on your screen, it's relatively easy to see that, whoa, what just happened here? Relatively easy to see that the spacing of the nodal lines and anti-nodal lines is much closer now. They're more closely spaced. So shorter wavelength, closer spacing, longer wavelength, and longer wavelength corresponds to a lower frequency, greater spacing. Let's confirm that again. So I'm going to decrease the frequency, which means longer wavelength, and we will also see that that means a larger spacing between antinodal lines or nodal lines. That's a behavior worth memorizing. In a moment, we're going to express that quantitatively, but right now we're just making a qualitative observation. Are you bored of this color scheme? Let's try a different one. Okay, that works. What else can we do? How about we change the source separation? Now I could just click and drag, but I may also be able to do that numerically. If I right click, go to edit. No, they're not actually giving us an option for that. So I'll just click and drag. Before I do that, memorize the spacing of the nodal lines there. Okay, so now the sources are closer together. Okay, the nodal lines definitely spread out. And that's a little counterintuitive. That might be the opposite of what you'd expect. Maybe the easiest guess would be greater separation of the sources would mean greater separation of the nodal lines, but the opposite occurs. So let me separate these further again. And we'll watch what happens to the nodal lines. Now they're much closer together. All right? So after you've seen it, it's easier to imagine it when we're looking at equations. The farther apart these sources are, the more bunched together the nodal and antinodal lines are. And while we're here, let's go to the actual two-slit interference pattern. So up here you see plane waves incident upon a barrier that has two slits in it. Can you see those two small slits in this bar here? Now, where would plane waves come from? Imagine dropping a giant anchor into the middle of the ocean repeatedly. So you plunge the anchor in, pull it out, plunge it in, pull it out, and you make these circular ripples in the middle of the ocean. And then they travel outwards for hundreds of miles, thousands of miles. By the time they get to a beach at the edge of a continent, the radius of those circles is so big that it almost looks like a straight line. So you can think of these plane waves here as coming from some isotropic source really far away. Now, practically speaking, if this was a light wave impinging on a barrier with two slits in it, this plane wave could actually be the interior of a beam from a laser. A laser looks a lot like a plane wave if you're within the beam. And the important observation here is that each slit behaves like a new source of waves. In fact, there are circular, you can think of it as circular or extend this to 3 dimensions, spherical. There are, I'll say circular, wavefronts emanating from both of these slits. So they each act like new sources which have an inherent phase difference of 0, right? Because the two slits are being driven by the same incident beam. So they start out in phase. So they're in phase in time, you could say. They have an inherent phase difference of 0. But as those circular wavefronts travel outwards, if I were to ask for the total amplitude of the wave right here, for instance, well, the two waves travel slightly different distances since the slits are apart from each other. And so there may be a path length difference that would introduce a phase shift. And you'll notice that this pattern is really no different in character from the two source pattern. We still have nodal lines and antinodal lines. Aesthetically, it looks a little bit different. Let's see if I increase the brightness. That's starting to look a little bit more, a little bit more like the previous example. And let's see if we can confirm the same behavior that we observed a moment ago. So I'm going to increase the frequency, which makes a shorter wavelength. What did we see for short wavelengths? The shorter the wavelength, the more closely spaced the nodal and antinodal lines are. Here I go. Shorter wavelength, and yes, the effect wasn't as pronounced, and that's probably because of the dimensions here being a little bit different than the two source example. If I go all the way up, yeah, that makes it pretty clear that a shorter wavelength means a closer spacing. So let me go back to somewhere in the middle of the range, and let's see if we can confirm the other behavior, which was changing the spacing. I'm not sure I can do that with this particular setup here. Yes, I can. I can control the slit width, and that's something we're not worried about in this presentation. Later, we're going to look at how the width of each individual slit affects the interference pattern, but right now we don't care about that at all. So the separation is currently 234 nanometers. Now, previously we observed that a shorter separation or a smaller separation actually spreads out the maxima and minima. So let me see if I can make this even smaller, like 100 nanometers. And what happens to the spacing between the fringes? So in SI units, we use nm for nanometer, but in this simulation, the lowercase letter n is fine. Did you see that? The nodal lines and antinodal lines are spreading out further now that I made the slits closer together. So that's the behavior that's a little counterintuitive. The closer the slits are to each other, the more spread out the interference pattern is. One interesting observation about the interference that we're looking at here is that the mere juxtaposition of two sources, equal amplitude, equal frequency, allows you to focus energy preferentially in some directions and not in others. You see, if you just had one source, you'd have radiation or energy radiating outwards isotropically, same intensity in all directions. But by introducing a second source and placing it near the first one, we can choose the directions in which we would like maximum intensity. So here we've got maximum intensity in the forward direction and also off in these two side directions. And we have no intensity along the dark lines, the nodal lines. So by choosing the slit separation appropriately, or perhaps even choosing the frequency of radiation, we can determine the directions in which the energy flows maximally. So if these were radio transmitters, for instance, you might choose those parameters so that the energy gets focused towards a highly populated city and not so much through the desert where very few people live. Now, real antennas have a significantly more complicated geometry than just two sources or two slits, but the idea is the same. Some of you are familiar with those Yagi antennas. It's like a bar with a bunch of crossbars, kind of in a V shape. They work the same way. Each of those antenna elements, those little conductors, are emitting electromagnetic waves, and all of those waves interfere in such a way that you get a lot of intensity in the forward direction and not so much in the backward direction. The math behind it is really the same as what we're looking at here. A few minutes back, I pointed out that each slit acts like a new source of waves. Both slits are being driven by that incoming plane wave, but they each act independently as a new source of circular wavefronts, at least in the two-dimensional case. We can carry that idea further with the so-called Huygens-Fresnel principle, often just called Huygens principle. And I freely admit I am not pronouncing the name Huygens correctly. If you look it up, it's not easy to pronounce. I think it's a Dutch name. So here comes an incoming plane wave, and the idea behind this principle, or the idea of the principle, is this. Each point on a wavefront can be thought of as a source of new waves radiating outwards. So that's not really drawn on these blue bars here, but take this middle blue bar. If each point were radiating circular wavefronts, this one radiating circular wavefronts, this one as well, and then you looked at the overlap of all the circular wavefronts which were emitted at the same time, you would actually be able to show that the overlap is another horizontal line on the screen here. Okay, so just imagine a bunch of circles that were emitted from all these points at the same time, and look at their overlap down here, and that overlap would be another line. So that's not very interesting. Using Huygens' principle to find the next wavefront, that's the overlap of the previous waves, using Huygens' principle to find that next wavefront for the case of a plane wave isn't particularly interesting. It just gives you another horizontal line there. But it does become interesting when you encounter an obstruction, a gap, a corner, something like that. Because now these points are no longer sources of waves because the light cannot pass through the barrier. Only these points become sources of new spherical wavefronts. So you can see this wave was just emitted a moment ago at the same time this one was emitted, at the same time this one was emitted, etc. This one was emitted longer in the past or farther back in the past, but at the same time as this one from the other source. And if we just pick any set of these circulars, any set of these circles, all of which were emitted at the same time, let's go with these. This one must have been emitted a while ago because it's moved outwards quite a bit. Same time as this one. Anyway, you can see the overlap here. It's not just a horizontal line, it has this overall shape. So the idea is, freeze time, take an existing wavefront like this one or this one and draw a bunch of circles to show the waves that will emanate from each of those new point sources. And it's not like there's actually an antenna there, right, or a source of light. The source of light presumably is off the screen, but you treat it that way, and the result that you get works. It successfully explains the interference pattern that you would actually see if you shined light through this gap. Okay, so it's kind of cool that you don't even need math to do this. If you're willing to get out a compass and a ruler and just take a whole lot of time making a careful drawing, you could actually predict, using this principle, what the so-called interference or diffraction pattern would look like on the other side of a gap or a corner. So you're going to hear these words a lot in the next chapter. Diffraction, interference. They're really the same thing. They're both just superposition. That's it. We like to use the word interference when we're talking about the superposition of waves from two different sources. We say that the sources interfere with one another constructively or destructively. So interference typically suggests you've got more than one actual source. We use the word diffraction if we're looking at waves from maybe a single source as those waves pass through a gap or around a corner. That's what we mean when we say diffraction. Diffraction of a wave through the gap, diffraction around the corner. But it's still kind of like interference because to explain it, we can imagine each of these fictional sources along a wavefront all producing their own waves and those waves interfering with each other. So whether you call it diffraction, interference, it's not that important. You just have to understand these are both superposition phenomena. Here's that awesome graphic that you've seen already for the hyperboloids in three-dimensional space, the hyperboloids of constructive and destructive interference from two sources emitting waves isotropically with the same amplitude and the same frequency. I showed you algebraically that in the plane, if you just project this onto a plane that contains the sources, I showed you that those nodal and antinodal lines are in fact hyperbolas. So revolve those about the axis between the sources and you would get those hyperboloids of constructive or destructive interference. Now, if you're over here, if you happen to be looking collinearly with the sources, you would see an interference pattern like this. And this is called an airy disk, those concentric rings of interference. And believe it or not, when you're looking at the light from a faraway star at night, that star may look like a point source of light. You might expect that the image of that star on your retina, that's the back of your eyeball, would also be a point, but it's really something like this. This is the pattern of light that strikes your retina when you're looking at a point source of light. So we'll talk about that more later. What we're interested in this presentation is this pattern right here. So this really is the far field interference pattern. If you had a screen really close to the sources, let's say, this is a couple inches separation between the sources and your screen was like half an inch away, you wouldn't see something like this. It would be a little more nuanced. But if you put your viewing screen far enough away, so if this is a couple inches and this viewing screen is like 20 feet away, then you would actually see these alternating bright and dark bands. And those are called fringes. Interference fringes. We've got the bright fringes and the dark fringes. They really just tell you where the antinodal hyperboloids and nodal hyperboloids are intercepting the screen. That's it. So it's the same phenomenon. These hyperboloids of revolution are the three-dimensional nodes, or nodal lines and antinodal lines. But this would be difficult to treat mathematically, right, in 3 dimensions. So we just look at the projection onto a screen like this. Excuse me. So the line joining the sources move off perpendicular to that line, go out quite a ways, and the projection of the interference onto that screen, that's what we're concerned with in this presentation. And being able to quantify the spacing between these fringes and the distance from the screen to the sources, that's going to allow us to determine the wavelength of the light. How cool is that? So I meant to actually start this presentation by saying that the simple math we're going to look at here will allow you to measure something accurately that's, let's see, 1/100th as long as the width of your hair. Can you imagine that? Have you ever used a measuring device that would allow you to measure something 100 times thinner than your own hair? I don't mean your hair thinning the way mine is. I'm talking about the actual width of a hair follicle. You can't do it with a ruler, that's for sure, because a ruler will get you to the nearest millimeter at best. Some of you have used a vernier caliper, which will get you easily to 1/10 of a millimeter, or even a micrometer, which will get you to 100th or even 1,000th of a millimeter. But we're going to see how interference of light allows you to measure something even smaller than that. And that technique is called interferometry. Okay, here's a screenshot of the double slit. Can we reconcile that with the previous slide, this slide right here? Okay, so I've flipped it around. I had to stretch it a bit. But there it is. It doesn't matter if your sources are speakers producing sound waves, or, I don't know, seismic disturbances within the earth that are producing waves of equal frequency. That seems unlikely. Or radio antennas emitting radio waves in phase at the same frequency. Or 2 slits being driven by a laser beam and then producing their own electromagnetic waves. It doesn't matter the nature of the sources. The pattern's going to be the same. So look at these hyperboloids of constructive and destructive interference. They correspond to these nodal and antinodal curves in the plane. It's the same thing. So if we had a screen here, when we were looking at the interference fringes, that would be the same as putting some screen up here, like so. So here's our viewing screen. And you can imagine that if you dimmed the lights in the room, so you've got your laser beam illuminating the slits along these nodal lines. See the black line? That's where the total amplitude of the electric field, or I should say the amplitude of the total electric field, is near 0. And we know that the intensity of light is proportional to the square of the electric field. We looked at the Poynting vector, right, for a plane wave. And so that means you would expect to see just a dim spot there. You're not going to see a bright laser spot. That would be a dark fringe, not a bright fringe. So yes, this color coding here is blue and yellow, but if this were a helium neon laser, for instance, it would be a red laser beam, and your fringes would be alternating bright red fringes and dark red fringes. Dark meaning, very little light. Okay. Aren't you impressed that I managed to get this image to line up exactly with the antinodal and nodal curves? So let me rephrase that. The antinodal curves, that's where you get maximum amplitude from the interference. That, when you let one of those antinodal curves intercept the viewing screen, you will see a bright fringe there. And let me point something out in addition. If you're watching this, you shoot the laser through the slits and you're looking at the interference pattern, it looks like you've just got solid brightness in time, constant intensity. But you have to keep in mind that this is an oscillating electric field. It's a sinusoidal wave. And so we've looked at the fact that the intensity is actually, the magnitude of the Poynting vector is oscillating trillions of times per second if you're talking about visible light. I think more than 10 trillion times per second. So if you could like slow time down by a factor of 100 trillion, you would actually see even the bright fringes go bright, dark, bright, dark. They would be oscillating in time with the magnitude of the pointing vector. But the dark spots would just be dark all the time. Okay, but in the real rate of passage of time, your brain and your eyeballs are nowhere near capable of seeing such rapid changes, right? Even 30 frames a second on a film screen is enough to trick your eye into seeing fluid motion. So you're certainly not going to see the fluctuations on the order of a trillionth of a second. Okay, let's flip this on its side now, because that's typically how this is done. Most of the diagrams you see will have the sources aligned vertically. And here are the symbols that we'll use. Lowercase d, that's the separation between the sources. And that's a pretty universal notation. For instance, Pasco, the maker of physics lab equipment, they use the letter D for their double slit apparatus. And capital L will be the distance from the sources to the viewing screen. And we're also going to use this coordinate y. So set up an axis, I guess I should just say an origin. The origin, as far as vertical coordinates is concerned, is the midpoint between the two slits. So here's my origin, and my y-axis is positive this direction, negative in this direction. So we'll use the coordinate y to locate the fringes on the viewing screen. That's where the coordinate y is relevant. We're not going to use the y-coordinate to describe anything between the slits, just the screen itself. We use the y-coordinate to locate the fringes. And let me back up. You'll notice here that this middle fringe, we're going to call that the y sub 0 coordinate. This first fringe off to the side in the positive y direction is y sub 1. Y sub 1 is the coordinate of the very center of the first bright fringe that's off to the side. And then, of course, y2 would, oops, where'd it go? Y2 would be the coordinate of the middle of the second bright fringe, the second one off to the side. You get the idea? Now, you can see already they're basically evenly spaced. And you also see that the intensity is dropping off as we move to the side. These are clearly more bright than these. That is a feature we will not be able to describe in this presentation. That's related to the slit width of each individual slit. So don't even worry about that yet. We are going to look at it. But if the the maxima way out here were actually bright enough to be visible, we would see that the spacing does start to change. So the spacing is really only uniform for the first several fringes away from the center. Okay, so we'll use the symbol y sub m to identify the location of the mth bright fringe. And the center one in the forward direction is y sub 0. We can call them bright fringes, or we can call them interference maxima. They mean the same thing. Now, what about the locations of the dark fringes, or the so-called interference minima, where you get the minimum light intensity? I'm not going to say 0. It may be close to 0, but it's not exactly 0 necessarily. And keep in mind, we're also not talking about the sensitivity of the human eye. Just because, like, what if the bright fringes in SI units are 10 times the intensity of the dark units? That doesn't necessarily mean that human perception will like if you ask somebody, does this look 10 times as bright? Like, to me, I would say, well, this looks like 1,000,000 times as bright as this. That ratio, 1,000,000 to 1, isn't necessarily the ratio of the SI intensities. Okay, so your book is using primed coordinates to locate the center of the dark fringes. Y1 prime is the coordinate of the center of the first dark fringe. And notice that there is no y prime 0 fringe, right? All the dark fringes are displaced from the forward direction. So we don't need to worry about y prime 0. Y2 prime, that's the middle of the second dark fringe. Okay. We would also like to find the formula for the location of the dark fringes, those coordinates. And you could probably guess don't they look like they're just halfway between the locations of the bright fringe? Once we find the expression for the y-coordinates of the bright fringes, it seems pretty clear that the dark fringes will just be midway between them. Further notation. Our screen over here, let's choose an arbitrary point on that screen and investigate the intensity of the light striking that screen. So what's the amplitude of the total wave there? We'll call that point P. So you can move this point around. And we're actually not going to develop the general formula right now in this presentation. It's really not difficult to do. We'll do that later. We can actually come up with a formula that describes the intensity anywhere. So not exactly at a bright fringe, not exactly at a dark fringe, but somewhere in the middle. So not on a nodal curve and not on an antinodal curve, any arbitrary point, we will have a formula for that intensity. Right now we're just going with the simple case of where are the bright fringes, where are the dark fringes. Okay, this picture kind of sucks because you'll notice that the wavelength that I just drew here does not match the wavelength in the Falstad simulation. That would have been a real pain to accomplish, but it's supposed to be the same wavelength. So the Falstad picture, if these were water waves, that's what it might look like if you were viewing it from above. This sinusoid here could be a little misleading. Again, it's symbolic, it's pictorial. It doesn't actually tell you that the electric field is oscillating this way, or if we were talking about sound waves, as the wave travels outward, it's not like the air particles are doing this. It's just pictorial. It's meant to represent how the displacement of the air particles, let's say, if we were talking about sound waves, or how the strength of the electric field varies with distance outwards from this source. That's all it means. So let's say a peak here would mean that the electric field has its maximum value, and a trough here would mean that the electric field now has its negative value. Now, where the electric field is pointing, there's a couple possibilities there. So don't take these peaks and valleys too literally. They are, however, supposed to show you the wavelength. So ideally, this wavelength would match the wavelength here between bright and bright. If we had labeled the sources S1 and S2, then the natural names for these distances would be R1 and R2. R1 is the distance from source 1 to the point at which we would like to know the total intensity, or the total electric field for electromagnetic waves. R2 is the distance from source 2 to the field point. Yeah, I'm going to call this point the field point. These are the sources, and P is the field point. We are interested in the path length difference. Remember the total phase difference between two waves of equal amplitude and wavelength, etc.? We have an expression for the total phase difference. There's a contribution from the inherent phase difference if they're being driven out of phase or in phase, and then there's the contribution from the path length difference. And usually we're talking about two sources which are already, quote, in phase, meaning they're in phase in time, or as your book would put it, they have an inherent phase difference of 0. So the only possible contribution to the phase difference would be from the path length difference. And just for this picture, you can see that these two waves are actually arriving out of phase. So I'm not referring to the speakers, or I should say I'm imagining light waves here. So I'm not talking about the sources of light. They're in phase in time, but the waves that they emit evidently are arriving at this point out of phase. The peak from one is lined up with the valley from another. Now, a half a period later, there's going to be a valley right here and a peak right here, but they're always canceling each other out. So this would be a point of maximum destructive interference, and you would expect to see a dark fringe there. Now, don't try to match that up with the actual Falstad picture on the background, because they probably don't match up. Now we're going to replace those sinusoids by just rays, because we're really just interested, for calculational purposes, in the distance. So I'm just going to represent that wave with a ray from the source to the field point, and that'll make it easier to analyze the geometry. And I've introduced an axis now here that is perpendicular to the axis of the sources. Maybe I shouldn't say axis of the sources. That's not a phrase that your book uses. The line segment joining the sources. Just bisect that with the perpendicular line. And over here is the origin for our y-axis. And we've already determined that there's a bright fringe in the forward direction. That's the y sub 0 location. Okay, what am I doing here? Well, observe what happened to the angle between these two rays when I went from this picture to this picture. This picture is misleading when it comes to our actual use of this phenomenon in lab. Like if we were actually going to measure the wavelength of light, this distance we'll see is going to be much less than this distance. So you put the viewing screen typically a couple meters, at least a meter away from the sources, maybe 2 meters, maybe 3 meters. And the location of the fringes is usually just a few millimeters away from the forward direction. So we're talking about millimeters compared to meters. So let me successively zoom out. Do you see how these rays appear to be more closely, or I should say more nearly parallel? They're not parallel, but they're definitely more parallel than they were in this picture. So the idea is zoom out even further. Here's an even more realistic representation of what you would actually see in a lab, because the separation between the sources is usually less than 1 millimeter. And this distance, like I said, is a full meter or even 2 meters. So this distance could be easily 1,000 times or 2,000 times the slit separation and this distance. Most of the fringes that we see are clustered very closely around the forward direction. So even this picture is misleading. By the time you're way out here, there's no light intensity at all. And the reason for that, like I said, we'll get to later. That has to do with the width of each slit individually. But forget about that for now. So even this picture is misleading. Hopefully you can see if you just continue this trend from here to here to here, eventually those rays are very close to being parallel. And that's the fact that we need in order to derive our formula for the location of the maxima and minima. Okay, so I've zoomed in now, and I'm just making the assumption that the field point is so far away compared to this slit separation that the rays are essentially parallel. Okay, well remember, capital L is the distance from the slits to the screen. This is the forward direction, right in front of the two slits. And the y-coordinate here would be 0, and now I'm using just some general y-coordinate for any field point on the screen. And I put the L up here so that you could more easily see that we're dealing with a right triangle. Now maybe you're thinking, well, not exactly, because it's like you've got two hypoteni over here. Yeah, but these rays are really close together. So just regard them together as the hypotenuse of this right triangle. And I'm surprised I've never done this before. We're going to invoke the small angle approximation. And I never actually picked a number to convince myself that it's a really valid approximation. Check this out. I mentioned that most of the fringes are within a millimeter or 2 millimeters, let's say a centimeter, of the forward direction. We're talking about just a few millimeters or centimeters right here. But the screen to slit distance, L, is something like a meter, 2 meters. So let's just go with 1 millimeter for the location of a particular field point, or the coordinate, and ask for the angle here, right? We've got the opposite side and the adjacent side as far as this angle is concerned. So in order to calculate that angle, we would take the inverse tangent, or the arctangent, of opposite over adjacent. That's 1 millimeter in the numerator over 2 meters, but 2 meters can be written as 2,000 millimeters. And the units cancel, so we're just taking the arctangent of 1 over 2,000, which is the inverse tangent of this number. And I encourage you to try this. I did this in my calculator, and I was surprised for a moment. I thought my calculator wasn't working, because when I hit equals, so I punched in this number, I hit inverse tangent, and the same number was still on the screen. Nothing changed. There were no extra digits after the 5, nothing changed. So I thought my calculator was broken. But what was really going on is, like I went into Maxima, a computer algebra system, and got more digits because my cheap $10 Casio only shows me something like 10 digits. And this is closer to the value of the arctangent of 1/2000th. So it's so close to 0.005 that if your calculator has to chop off right here, let's say, it's just going to round up to 0.0005. You should try it, because then you won't have any doubt about the validity of the small angle approximation in this setup. You should also check the sign of that number. So this is the angle, right, in radians. If you take the arctangent of y over L, what comes out of the arctangent function is the angle. Right? You put the ratio in, the angle comes out. That's different from the tangent function. With tangent, you put the ratio in. No, you put the angle in, excuse me. For tangent and sine and cosine, you put the angle in and a ratio comes out. Here I put the ratio in, opposite over adjacent, and the angle came out. So let's also ask for the sine of that angle. What is the sine of 0.000, etc.? Well, you can't put this whole thing in your calculator because you may not have that many digits. But the number that comes out is also practically the same. 1, 2, 3, 4, 5, 6, 7. The first 7 digits are identical. Okay, so I hope I've convinced you that the angle in radians, that's this number here, is very close to being equal to the sine of that angle, right? This is the sine of the angle. This number in parentheses is the angle. And the tangent of the angle would be the 1 over 2000, which is 0.0005. All three of those numbers are super close to each other, so you're totally justified in interchanging them, because the error involved in using theta rather than the tangent of theta, or in using sine of theta rather than tangent theta. I mean, look at the difference between the sine of theta, that's this number, and the tangent of theta, which is 0.0005. They're practically the same. The error introduced in making that approximation is evidently, let's see, this is the tenths place, hundredths, thousand, million, 10 million, 100 million, billionth, 10 billionth. I'm losing my train of thought. 100 billionth, a trillionth. Oh my gosh. So the error is something like 1 trillionth. Isn't that way smaller than the other sources of error? Like if you're doing this lab in a classroom, your lab partner is going to screw up way worse than that 1 trillionth. So totally negligible source of error. Okay, so to summarize, as long as the lateral spread of those fringes is much less than the distance from the slits to the screen, this is a great approximation. It's almost not even an approximation, right? It's not even really the appropriate word to use. That's why I almost feel like this squiggle equal sign is misleading, because it gives you the impression that they're like sort of equal. They're really close to being equal. Okay, y over L, that is opposite over adjacent. That is the tangent, right? The opposite side divided by the adjacent side of that triangle is the tangent of the angle, and we know that the tangent of the angle is really close to the sine of the angle. Now, I don't know why I did that here. What's the difference between these two symbols? I'm not really sure. Okay, so what we're using here is called the small angle approximation, also called the skinny triangle approximation, and you can look at it graphically. This is a graph of sine, cosine, and no, not cosine. X, y equals x, that's the line that makes a 45-degree angle with the x-axis, or the sine of x, that's the green one, or the tangent of x, that's the blue one. So they're all going to diverge quite a bit as you move to the right, but near the origin, they're super close together. You can also look at their Maclaurin series expansions about theta equals 0. Here they're using the letter x, here they're using theta, whatever. And you see that sine and tangent have the same first term in their Maclaurin series. Moving on. We make the assumption that these rays are parallel, and check it out. This spot, whoops, I'm jumping the gun here. This is the angle theta, right? Since they're parallel virtually, then they both make the same angle with this direction, you know, the forward direction, perpendicular to the line joining the sources. Same angle theta. So I could have drawn right here also the angle theta. And do you see that this bottom ray is the one that has to travel a little bit farther. It's got this extra red distance to travel. If you just imagine both rays starting from here, here and here, they're going to meet at the field point. So from here on, they travel the same distance. And I know you're thinking maybe, wait a minute, they're not really parallel, right? If they have to meet at a point, then these rays are going to be tilted towards each other. That's true. But if the point is far enough away, then at this scale, the scale of this picture, they look like they're parallel. So this is the extra distance that the bottom ray has to travel. That is delta R. We need to know what delta R is so that we can use our previous formulas for the conditions for maximum constructive or destructive interference. Well, that's easy to do because we've got a right triangle. Anytime you can find a right triangle, you can probably do something useful with it. Okay, I'm not going to try to show this as if we're in a high school geometry class, but this angle also has to be theta. One way to see that is take these rays and bend them down towards the horizontal. So basically shut this angle down to 0. And you can see that as you shut this angle down to 0, this angle would also close up. So if they open and close together, they're probably the same angle. Is that compelling for you? Is that a proof? Look how easy that was. Take this right triangle. The slit separation is the hypotenuse of this right triangle, D. So take the hypotenuse, multiply by the sine of the angle, and that will give you the opposite side, the path length difference. So there it is. We can very easily express the path length difference in terms of the separation of the slits and the angle. So as you're looking at greater and greater angles away from the forward direction, you're talking about a greater and greater path length difference. It makes sense, right? If you bend these lines down to the forward direction, then your two rays would be traveling the same distance. There's no path length difference. And that's what the formula is telling us. When you plug in theta equals 0, you get out that delta R is 0. Okay, so the greater the angle, the farther the bottom ray has to travel. So the greater the path length difference. Okay, you've seen this before. I know you have because I went over it way too many times in a previous presentation. I'm sure it was super boring, but now it's paying off. We know that the total phase difference between the two waves, so this is not, I wouldn't say this is the phase difference between the sources. Usually if we talk about the phase difference of the sources, we really mean the inherent phase difference. We're talking about the phase difference between the two arriving waves at a particular point. There's a contribution from the path length difference and the inherent phase difference from the sources. But usually, when we're doing double slit interference, we imagine that the slits are being illuminated by the same source of light, like a laser beam, so there is no inherent phase difference. So we just get rid of that. You'll notice there's a factor of 2 pi on both sides. By the way, I should back up. Remember, we need the overall phase difference to be 2 pi, 4 pi, 6 pi, etc. if we want max constructive interference. Okay, let's get rid of the 2 pi's. And notice I also got rid of delta phi. As soon as you divide by 2 pi, you're no longer talking about a phase difference in radians. I'm dividing out those 2 pi radians. And this is the simple condition that I should have emphasized a little more in previous presentations. If the inherent phase difference, delta phi sub 0, is 0, then the condition for constructive interference becomes really simple. It merely says that the path length difference has to be an integer multiple of wavelengths. That's it. Now, it could be a negative number actually. Yeah. A negative number would be fine as well. So you could even throw in -1, -2, but you'll see right now we just care about absolute values. So to summarize, as long as the bottom wave is traveling 1 wavelength further to get to the point, or 2 wavelengths, or 3 wavelengths, then the 2 waves will still arrive in phase. That's the basic idea. We don't need to worry about the inherent phase difference if the 2 slits are being illuminated by the same source of coherent light, like a laser beam. And if you ask me what coherent means, honestly, I still don't have, it's like I kind of know what it means, but I don't have a good way of explaining it. I don't have a good definition. So let's just think of it as that the slit's being driven by a source of light like a laser beam. I guess you could say this. If they were being illuminated by a light bulb, you probably would not see this effect because a light bulb has a bunch of little bursts of light in it from all the various particles in the filament. They're not. It's not organized oscillation the way a laser is. So we would say it's incoherent light. Also, it's light of different colors. That's another important point. We're talking about light of a single wavelength. That is called monochromatic. Monochromatic means one color, literally. So we're just talking about a single frequency. And a laser is really good at that. A light bulb sucks at that. Light bulbs put out a whole spectrum of colors, and practically all the colors of the rainbow, much like the surface of the sun. Okay, so we've established, oh, let me add one thing. If you're in the forward direction, the point right here has the waves arriving with no path length difference, so you get constructive interference. As you move away from the midline, eventually you're going to get to a point where the path length difference is exactly one wavelength. That's the y sub 1 bright fringe. Then they're interfering destructively again, eventually get to a point where now the second wave had to travel 2 wavelengths farther. You get another bright fringe. Destructive again. Then you get to a point where the bottom wave had to travel 3 wavelengths farther. Again, that's a bright fringe, constructive interference. Same thing would happen on the other side of the forward direction. Okay, let's put this stuff together. We used some simple geometry to find the path length difference in terms of the slit separation and the angle to the field point. We used our previous condition from a previous chapter about the conditions for constructive interference. So here's where we use the small angle approximation, right? I've already convinced you that the sine and the tangent, they're basically the same, out to like the trillionth digit maybe. And then the tangent of theta, that's what we can express in terms of the y-coordinate of the fringe, or the y-coordinate of the field point, I should say, and the slit to screen distance. So let's replace the tangent of theta by opposite over adjacent. And now I'm assuming that the y-coordinate we're talking about is a position where we get max constructive interference. In other words, it's one of those bright fringes. So that's why I'm using the special y-coordinate y sub m. Take all this junk and plug it in here. And you get this formula. And we're so close to the end now. Because what are we actually interested in? It depends on the homework problem you're doing, or the exam problem, or what you're seeking in your lab environment. So right now, we're looking for the y-coordinates of the bright fringes. We would like to predict where those fringes will be located, the middle of the fringes. So let's solve this for y sub m. And there it is. That's the formula that you might want to commit to memory. Definitely have it on your note card. You know what's even cooler than either of those is if you understand how to get it. That's really the best you can do. It takes just a little bit of time, less than a minute though. If you know what you're doing, you can arrive at this result very quickly. And that's probably the goal for some of you. But have it on your note card anyway, right? Okay, so plug in m equals 0, and you would of course get 0 for the 0th fringe. That's the one in the forward direction. So its y-coordinate would be 0. You plug in m equals 1, and you get that first bright fringe where the bottom wavelength, or the bottom wave is traveling one more wavelength through space. When you plug m equals 2 in, you're getting the location of the next bright fringe. That's where the bottom wave had to travel 2 wavelengths farther. And here's a nice way to think about this formula that helps me memorize it. Look at what we've got here. You're taking a ratio of 2 distances, so it's dimensionless, right? Wavelength compared to slit separation is a dimensionless quantity. And let me point out that this ratio is much less than 1 usually, because the type of slit separations we're talking about normally are, half a millimeter, a tenth of a millimeter, probably more like a tenth of a millimeter. But visible light has a wavelength of, 500 nanometers, a way smaller number. So this ratio here is always, I shouldn't say always, but it's usually much less than 1. In fact, it's basically always much less than 1, because if it was approximately equal to 1, then it turns out that this approximation wouldn't be very valid. I'd have to think about that. But for most of our purposes, this is much less than 1. And then we're scaling it by a factor of L. So the relevant ratio here is how long the wavelength is compared to the slit separation. That's the important behavior. And we just scale that by the slit separation. That makes sense, because if we put the screen half as far out, imagine the screen was right here. Look at the direction of these rays. This is where the first point of constructive interference is on this screen. But if we had the screen here, that first point of constructive interference would be here, not here. So the distance of the fringe from the forward direction, if we had the screen here, is about half of what it is here. That's what we can see in this equation. The lateral location over here of the fringes depends on how far out you're looking, where you put the screen. The farther out you put the screen, the more you scale up the separation of the fringes. And that's really easy to observe in the lab. You slide the screen towards the source and you see all the fringes start to bunch together. But this is the important ratio, because we're going to see that one reason we observe this behavior for light and not so much for sound. No, I take that back. You do actually observe this sort of thing for sound. The reason why you don't see this when you shine a laser pointer through a door, like imagine being inside a room with, I don't know, 2 doors close to each other. That's silly. How about 2 windows? You're in a room with 2 windows close to each other and you shine a laser beam at the windows. You're not going to see interference fringes on a wall outside those windows. This only happens when you shine coherent light through very narrow slits. So this is something we'll emphasize later, but you only get the interference when the wavelength is comparable to the slit separation. If the wavelength were way less than the slit separation, let's think about that. Yeah, if lambda was so close, like if it was an X-ray or an ultraviolet, so a number way smaller even than 500 nanometers, each of these y coordinates would be so small that all the fringes would be bunched up and just look like a single dot. Yeah, I think that's what you would see. So if the wavelength is too small compared to the slit separation, all the fringes kind of get bunched together and there's not a whole lot to see. It just looks like a blurry dot. You need to spread them out a little bit to see it. And that means that lambda needs to be closer in value to d. It's still less than d, but it's not like a trillionth of d. Okay. One more observation here. Let's plug in the first 3 integers. I skipped y sub 0. Okay, 1 times lambda over dl, 2 times lambda over dl, etc. So what's the distance between 2 adjacent bright fringes? Like the distance from the second bright fringe off of center to the third bright fringe. You would just subtract these 2, and of course, you find that common difference, lambda over dl. So lambda over dl shows up in the formula for the mth fringe, but lambda over d times l is also the separation between 2 adjacent fringes. And that's also very useful to keep in mind, because in practice, you're probably going to just measure the distance between 2 adjacent fringes in the interference pattern. So you would plug in delta y, and you could solve for lambda. As long as you know the distance between your screen and your source, that's easy. And as long as you know the separation between the slits, that's something the manufacturer would provide if you were doing this in a lab, then you just have to measure the distance between the fringes, and boom, you've determined the wavelength of light. How cool is that? Because we're talking about, again, distances much shorter than the width of your hair. And you can measure it just by using the interference phenomenon that we've been talking about for a few weeks now. Okay, here's an actual picture of the interference pattern, the fringes from a laser that's shining through, it looks like two slits. Now, as I pointed out, there's some more subtle behavior here. Instead of just saying bright fringe, dark fringe, bright fringe, dark fringe, we're actually seeing an overall modulation of the brightness. That cannot be explained until we look at the diffraction of light through a single slit. That's a topic for later. So all we care about right now is the fact that we've got bright, dark, bright, dark. So when I say bright, dark, I'm not talking about bright, dark, bright, dark. That's different behavior. I'm talking about bright, dark, bright, dark. Okay, delta y is the distance between the centers of two adjacent fringes. And you see how it's the same, right? This separation is the same as this separation, is the same as this separation, etc. Here's the formula that relates the separation of the fringes to the other relevant parameters. Now, if you wanted to get a more accurate determination of delta y in a lab, it's difficult to measure something like a 0.5 millimeter precisely. Wouldn't it be better to measure the total length of several fringes in a row and then just cut that down by the number of fringes? So here's an example. Let's measure this total distance with your ruler. If you were in a lab, you'd go from the center of this fringe, because you can still see that one, to the center of this fringe. And that's a total of 1, 2, 3, 4, 5, 6, 7, 8 adjacent fringe distances. So I would measure that whole distance with my ruler, divide it down by 8 to get the separation between two adjacent fringes. And that tends to reduce error, of course. So that's a better way to do it in lab. Let me point out that it almost looks like we've got a long sequence of equally spaced fringes. There just happens to be a couple missing. Like these two seem to be missing. There's one almost missing here, one missing, definitely one missing here. Those missing maxima, again, are a consequence of the diffraction phenomenon when you talk about light passing through a single slit. And we'll look at that later. But I should point out now that those are called missing maxima, or missing orders sometimes. What's going on here? Well, it depends on the lab you're doing, but very often you're doing this to measure the wavelength of light. And it's kind of contrived because you do this experiment with a laser that you bought from a manufacturer, and they tell you right there on the laser what its wavelength is. But it's fun to confirm the value. So solve this for lambda, and it tells us that the wavelength of light that we measure is proportional to the separation of the slits. Not the slits, excuse me, that's D. The separation of the bright fringes. That's what I'm using the symbol delta y for. So this distance right here. That means as if you're looking at an interference pattern with a greater separation between the fringes for a given slit separation, then you're talking about a longer wavelength. So just imagine you've got the same experimental setup as far as the slits go. You've got an opaque barrier with precisely machined slits from the manufacturer. Actually, it's really a film with the coating, I believe. And so first you shine a red laser through it, and you observe a particular separation between the fringes, and then you swap that laser out for a blue laser, which we know has a shorter wavelength. And if the wavelength is shorter, but we haven't changed the slit separation, then we're going to expect a more closely spaced fringes, because we know that the wavelength is proportional to the spacing of the fringes. So I've tried to represent that here. Blue light has a shorter wavelength. That's why we're seeing less separation between the fringes for the same slit separation. Back to the ripple tank once more to confirm those observations for a second time. And this time, instead of the double slit, I went with the two-source configuration, because remember, it's the same. It doesn't matter whether the two sources are slits being illuminated by a laser beam or isotropic radiators of radio waves. The only difference there would be the wavelength. Let's go with something a little more festive for the color scheme. I like this one. And just to be a little more consistent with the actual picture, I take that back. Normally the double slit is oriented this way. So let me drag these to the left of the screen. And we will imagine that the screen, not my computer screen, but the viewing screen for the experiment is over here on the right. And these fringes are really spread out. Can you see this would be the forward m equals 0 fringe. This is the m equals 1 fringe. And the other m equals 1 fringe. I probably should have pointed that out by now. It doesn't matter which side of 0 you're on. The numbering scheme is the same. So this is m equals 1 above and m equals 1 below. This one, m equals 2, is almost at 90 degrees. So you won't even see that one on the screen. It's never going to make it to the screen, right? It'll just go up and miss the screen entirely. So if I'd like to bring these fringes together, have more bright fringes show up on the screen, then what was the relationship? I think shorter wavelength also means shorter spacing between the fringes. Well, a shorter wavelength implies a higher frequency. All right. So several of those fringes should be visible on the screen. Is that hurting your eyes? This is a little better. This would be the forward or m equals 0 fringe, m equals 1, m equals 2, 3, etc. And maybe you can see how eventually, as you move away from the forward direction, the spacing is going to change. But in this middle band, the spacing is pretty uniform. If you take these antinodal curves that you see and revolve them in space around the forward direction, you would get those hyperboloids of revolution. Hyperboloid! What was the other observation we made? Let me go back to something in the middle as far as the spacing of the fringes. The other observation that we made was the relation between the slit separation and what was the other one? The spacing of the fringes as well, right? So this is the one that had the counterintuitive result. If we spread the sources apart, or equivalently spread the slits apart from each other, then the spacing will actually decrease. Let's confirm that right now. I'm going to put one of these sources farther from the other, and we have to wait for the field to update, so to speak. And yes, it's pretty clear that the fringes are now close together. If we want to really spread those fringes out, let's put the slits very close together. Okay, so there's only one broad central bright fringe. This is that m equals 0 fringe. The m equals 1 fringes go straight up. They're not even going to appear on the screen. And this is almost exactly the way a diffraction grating works. It's an unfortunate name. They probably should call it an interference grating, because it has to do with interference between multiple sources. We'll talk more about diffraction gratings later. But in a diffraction grating, you've got a whole bunch of slits, much like a double slit, but the slit spacing is really small, much smaller than a millimeter. You know, it's on the order of microns. And so if you shine a laser through one of these diffraction gratings, you actually do see the maxima spread out like this. If you were holding a laser in front of you and you shined it through the diffraction grating at a whiteboard, you would see one dot, just one dot from the laser beam, and then one way over here as well, and nothing in between. So for a really tiny slit separation, you get the maxima being really far spread out. And in that context, they're usually called orders. Orders. This would be the m equals 0 order. Over here off to the side, the m equals 1 order. As far as calculating the location of the dark fringes, that's the interference minima, we've done most of the work already, so we'll just kind of gloss over this. If you go back to the condition for max destructive interference, you'd see that the total phase difference has to be an odd multiple of pi. That's pi, 3 pi, 5 pi, etc. But because there's no inherent phase difference, that condition reduces to the requirement the path length difference must be not lambda or 2 lambda or 3 lambda, because that would give you constructive interference. The path length difference must be a half integer multiple of the wavelength. In other words, half a wavelength, or 1.5 wavelengths, or 3/2 wavelengths. And that's what this formula gives you. If you plug in 0, 1, 2, etc. for m, the numbers that come out are 1/2, 1.5, 3.5. I'm sorry, not 3.5, I should say 3/2. Yeah, let me say that again. 1/2, 3/2, 5/2, 7/2, etc. Or you could say, 0.5, 1.5, 2.5, same thing. So here are two different ways of saying it. You need either a half integer multiple of a wavelength, that's 1.5, 2.5, 3.5, 4.5, etc., or you need an odd multiple of a half wavelength. Two different ways of saying the same thing. Here is the latter way that I just named. This is 1/2 times lambda over dl, 3/2 lambda over dl, etc. Actually, this is the formula that you would wind up with regardless. So I'm using this scheme, and I'm evaluating it for m equals 0, 1, and 2, and I get these first three coordinates for the interference minima. These are the dark fringes. Remember, there's no m equals 0 dark fringe. The forward direction is a bright fringe. And your book likes to use the apostrophe or the prime for the minima. Okay, so really you just need to remember this condition, that the path length difference, which is d sine theta, has to be an odd multiple of a half wavelength. The spacing ends up being the same. You can see that right here. Also, isn't this what we expected? We've already found that the maxima are located at 1 times lambda over dl, 2 times lambda over dl. And from the graphics at the beginning, we predicted, or I predicted, that the minima should be halfway between, and that's exactly what we're finding. And when it comes to crunching numbers or doing problems, here's another useful observation. Whatever units you plug in for lambda will come out for the fringe spacing. Am I saying that right? Well, let's suppose that you measured L and D in the same units. Like if D was 1 millimeter or half a millimeter, and L was 2,000 millimeters, which is the same as 2 meters, then those units, millimeters and millimeters, would cancel. And so whatever units you used for lambda would come out the same for the spacing. That's actually not very convenient, because usually wavelengths are on the order of nanometers, and the spacing is on the order of millimeters. Okay, so here's a better way, or a more useful observation. If you measured the fringe spacing in millimeters and the slit screen separation in millimeters, then whatever units you plug in for D will be the units that come out for lambda. So oftentimes the slit separation is on the order of micrometers. And if you plug in micrometers, then micrometers will come out for the wavelength. So visible light wavelengths are conveniently described using nanometers or micrometers. Usually people talk about nanometers, but here's something I like to keep in mind. The human hairs are around 50 micrometers. And believe it or not, you can measure that with a micrometer caliper. I did this one time at a different school. Everybody in the lab measured their hair thickness, and there was actually quite a range of thicknesses. Some people had hair strands that were around 20 or 30 micrometers. Some people were up at 80, and that may have something to do also with the shape. Some people have flat ribbon-like follicles, and other people have... Am I using the word follicle right, or is that the root? I'm talking about the strand of hair itself. For some people, it's cylindrical, and other people's it's more like a ribbon, and I guess that is responsible for curling. But a hair is pretty skinny, and it's only 50 micrometers. We're talking about visible light. I looked this up. Cyan is almost exactly a wavelength of 500 nanometers. So let's just call that blue-green light. 500 nanometers is the same as 0.5 micrometers. So Nano means billionth, right? 10 to the negative ninth. Let's use 3 of those negative powers of 10 to move the decimal point from here to here. So we've already used up 3 of the negative powers of 10. Now we've got 10 to the negative sixth. That's a millionth of a meter, or 1 micrometer. So half a micron. There it is. Hair is on average 50 micrometers across. The wavelength of visible light is half a micron. 50 is 100 times greater than 1/2. So you could stack up 100 wavelengths of light across the thickness of a strand of human hair. Impressive that we can measure it, right?